Hey guys, welcome back to chapter 11. So what we're going to talk about today is vaporization and vapor pressure. This is included in our properties that are being affected by intermolecular forces, but because vaporization is such a, not difficult, but there's just more to the vaporization process, I wanted to give it its own video so we could really understand the vaporization process and then relate that back to intermolecular forces. So the first thing we're going to talk about is what is vaporization? So vaporization is the process of a substance going from a liquid to a gas. So the particle going from the state of a liquid, breaking all of those intermolecular forces, and then being released as a gas, able to free to move around without any involvement from somebody else. So how does it overcome those intermolecular forces? It does so with thermal energy. So it heats up, it overcomes the intermolecular forces, and it changes state. Okay. So this is a key statement here. The only particles that are available to vaporize are those at the surface. So you will not see during a normal vaporization process, let's say this molecule right here traveling all the way up and out as a gas. With it being down here in the middle of this beaker, it is not available to vaporize. The only particles that are available for vaporization are these guys right here at the surface. So that's a really key thing to think about. So what are some ways that we can affect this vaporization process? What are some ways that we can increase vaporization, decrease vaporization? And we can think about this also through intermolecular forces. So the first thing, what affects vaporization? Well, how would temperature affect this? So if we were to increase the temperature of this beaker of water, for example, increasing the temperature would increase the kinetic energy. If we increase the kinetic energy, if those particles start moving faster and faster and faster, what we're going to see is that there's more particles that are going to become gas. So with the increase in temperature, the increase in energy, we've got to do less work to break those particles free. So by increasing the temperature, we increase the kinetic energy, and we increase the number of particles that become vapor. Okay. Same thing if we cool it down, we decrease the temperature, decrease kinetic energy. There's not going to be as many particles that become a vapor. Surface area. So if we think about the surface area is going to be the number of particles that are available to become vapor, right? So if we're looking at the number of particles in this beaker, how many particles are available to become a vapor? Oh, just these right here at the top of the surface. What if I were to take that beaker and I were to spill it all over the counter? So if I spill that beaker and it spreads out over the length of the counter, now I've increased the surface area. What does increasing surface area do? It increases the number of particles that are at the surface, right? So it increases the number of particles that are available to become a gas. So if we increase the surface area, increase the number of molecules that are available, this is also going to increase the number that are vaporized. Okay, so we can increase the temperature, more things vaporize, increase surface area, more things vaporize. Okay. The last thing that we can do to affect vaporization is talk about intermolecular forces. Okay. So if we have a stronger intermolecular force, so in here, water's got a pretty strong intermolecular force, right? In here, these particles are holding on to each other fairly tightly. They're interacting strongly. These particles at the surface are going to be less likely to let go, or we're going to have to put in more work in order to break those intermolecular forces. So something that has a high intermolecular force, like water, would not have very many particles that vaporize. That's as opposed to something that would have a low intermolecular force. So something that has a lower intermolecular force, those particles are not holding on as tightly. We don't have to do as much to break those particles free. So they'd be more likely to vaporize. So we'd have more particles becoming vapor. A quick example of this would be water versus acetone. So if you spill water on your skin, it is going to evaporate a little bit. So that's how our body cools itself down. It puts sweat on our skin, sweat vaporizes, and we cool down. But it's not a really dramatic sensation, right? So if I put a little bit of water on my hand, it feels a little bit cooler, but not dramatically cooler. But think about putting something like acetone on your hand. So acetone has significantly lower or weaker intermolecular forces. So when you spill acetone or fingernail polish remover, paint remover on your hand, you get a really cool sensation right away. Well, that cool sensation is because that acetone is vaporizing very, very quickly. And your skin feels cool when it vaporizes on your skin. So acetone, low intermolecular force, lots vaporizing very quickly. Water, high or strong intermolecular force, does not vaporize as fast or as much. Okay. So that's the vaporization process. And that's different things that we can do to affect the vaporization process. We can talk about the energetics of vaporization. This is going to tie back into chapter 9 when we talked about enthalpy. So vaporization requires an input of energy to overcome the attraction between particles. So remember, in a liquid, those particles are very close together, interacting and attracted to one another very strongly. In order to go from a liquid to a gas, we have to break those interactions and essentially free that particle from the intermolecular forces. In order to break those attractions and free that particle, it takes an input of energy. It costs us something. So vaporization is an input of energy. Something that is volatile evaporates easily. So in our example, we would say acetone is a volatile substance. It goes ahead and vaporizes very quickly without us having to do much. So it evaporates easily. Something that is non-volatile, like water, does not evaporate as easily. Okay, so we would have to input more energy. It doesn't just do it on its own. When something vaporizes, energy exits the liquid and the temperature will decrease. So vaporization is an endothermic process. We have to figure out what position we're taking here, okay? So if I am the liquid, okay, I am the liquid, I am going to have energy put into my system, or energy is going to enter into my system in order for vaporization to take place. So I'm going to have to be heated up. That's going to break those intermolecular forces. And now I'm free to become a gas. So vaporization, if I am the liquid, is a endothermic process. Condensation is the opposite of vaporization. So condensation is going from a gas back to a liquid. So if I'm a gas floating around, I'm going to have to be an exothermic process. So I'm a gas floating around. I'm going to have energy exit my system or go somewhere else in order for me to condense back down into a liquid. So if you think of condensation, dew on the grass in the morning, it's because the air temperature cooled down. So the water that was evaporated as a gas cools down, energy exited. Now it becomes a water again. We see droplets all over the grass. Okay. When we quantify this, so this was kind of the qualitative endo-exothermic qualitative. We talk about it in theory. When we quantize this or we put numbers to it, we talk about it as heat of vaporization or the enthalpy. So just as a refresher, delta H is the enthalpy. Enthalpy is the fancy word that we use for heat, and heat is the type of energy that we study as chemists. So when I say the change in enthalpy, I'm saying the change in heat, I'm saying the change in energy. So did energy increase? Did heat increase? Did enthalpy increase? Or did energy decrease? The heat decreased. The enthalpy decreased. So that's how we think about this idea of enthalpy. So the amount of energy required to vaporize is this, this whole thing right here. So the enthalpy of vaporization. If enthalpy, and it is, but if, vaporization is endothermic, that means the change in enthalpy will be a positive number. Endothermic heat enters into the system. So for something to go from a liquid to a gas, we're going to have to put energy into that system. It's going to be a positive number. Condensation, on the other hand, would be a negative number. So for something to condense from a gas back down to a liquid, we have to take energy out. So the enthalpy would be negative. So just some examples. I've used a couple of these examples in my discussion, but just some examples of some chemicals, looking at their boiling points, and then looking at their vaporization, their heat of vaporization here. One thing I do want to talk about here, we see that this is condensation, vaporization is equal and opposite. So what that means is if I have to put in 40.7 kilojoules of energy per mole to cause water to vaporize, that means I would have to take out 40.7 kilojoules per mole of energy for that to condense back down. So this condensation, vaporization are equal and opposite processes. So I put in 40.7 to vaporize. I have to take out exactly 40.7 for condensation. So equal and opposite there. Okay. So all of that discussion to finally get to vapor pressure. So vapor pressure is going to be finally their property that we're going to discuss in terms of intermolecular forces. But I couldn't tell you, or I couldn't talk about vapor pressure if you didn't understand the vaporization process. So vapor pressure is going to be caused by the vaporization process happening in a closed system. So here we see a sample of water, but the difference is this isn't an open beaker anymore. This is a closed container. Nothing can escape. It's a closed system. So what we see here is we're going to start with a sample of a liquid. For example, I think this is water. And we're going to see that the rate of vaporization is going to increase. So we've got no vapor whatsoever. So water is going to start to vaporize. It's going to go from a liquid to a gas. So vaporization starts. Then at some point, we're going to reach kind of the maximum amount of vapor that can exist inside of this closed container. So far we were going from liquid to gas, going up, up, up. Now we've reached some sort of arbitrary maximum amount. And what we're going to see is no more vapor can be held. Then what we're going to establish is something called a dynamic equilibrium. We're going to talk so much more about this. We have a whole chapter on equilibrium. But let me just quickly introduce this idea. So this equilibrium tells me that there's going to be some particles that are escaping from liquid and going into a gas. And then there's going to be some particles that are like, you know what, it's getting too crowded up here. I'm going to condense back down into a liquid. So this word dynamic means we're going back and forth. We're vaporizing, condensing. Equilibrium means the rate is the same. So when I take a snapshot of this last beaker, the amount of vapor, the amount of liquid is never going to change, but the individual particles may. So this guy may be vapor, this guy may be water, and then they switch places. So that's what a dynamic equilibrium is. Okay. No net gain or loss. So that's kind of the defining moment in a dynamic equilibrium. Is it's dynamic, we're still going back and forth, but their processes are equal and opposite, so there's no net gain of liquid or no net loss of liquid. They've reached this kind of equilibrium. Vapor pressure would be the pressure exerted by the gas in this case, because this is a closed system. That gas is trapped in that closed container, then the vapor pressure would be the pressure exerted by that gas. Okay. And that's what this slide says. I got a little ahead of myself there. So the pressure exerted by the vapor during dynamic equilibrium is the vapor pressure. So now let's relate this to intermolecular forces. So let's say I have two flasks here. I've got a flask of water, it's closed. I've got a flask of acetone, it's closed. Well, which one would have the higher vapor pressure? So let's talk our way through this. Something that has a weaker attractive force. So a lower intermolecular force. So the interaction between the particles in here is going to be a weaker interaction. That means these particles are going to be a little bit more likely to vaporize, right? So their friends aren't holding on to them nearly as tightly. So they're a little bit more free to escape and become a gas. So if we have a weaker intermolecular force, we're going to have more particles as vapor. Okay. So if we have a weaker intermolecular force, we have more particles that are a vapor. What's going to happen to the pressure? What's going to have an increased pressure? There's going to be more particles up here that are exerting a force. So weaker intermolecular forces, more particles that are going to be vapor, the higher the vapor pressure. The opposite is true, okay? So if we're looking at this container and whatever molecule in this container has a high intermolecular force, so the attraction between the particles as a liquid is a really, really strong attraction. That means these guys down here are going to be pulling pretty hard on their friends. Their friends are going to be less likely or less able to become a vapor. So we're going to have less particles as vapor. Okay? So stronger intermolecular force, less particles that have the ability to become a vapor. So the vapor pressure is going to be a lower pressure. There's going to be less particles exerting a pressure. Okay. So that's the last property that we are going to observe based on intermolecular forces. The rest of this chapter discussion is going to go into melting and boiling and looking at phase diagrams of phase changes. I hope you guys found this helpful.